David Smith here with one more flipped classroom math lesson. 3 tips before we start. First, remember that you can adjust the playback speed faster or slower as you desire. Second, you can pause the video at any point to jot down some notes or write down some questions for our next class. Lastly, you could turn on the captions so you can read my words go by on the screen. Today's topic, limits at infinity. So up till now, we've taken the limit of a function as x approaches some number, some constant. So now we're going to see if a function has a limit as x approaches infinity. In other words, gets bigger and bigger and bigger, gets really big. And remember, we have negative infinity and positive infinity, so we can go both ways with that. So let's take a look at one of those functions and watch what it does. Here's my function, f of x equals x plus 1 over 2x. Now let's take a look. As x gets really big, let's say x is 1,000. This is 1,001 over 2,000. So this is getting really close to 1/2. It's always going to be a little bigger on the top that would make it 1/2, but it's going to get really, really close. Now as x approaches a really big number from the negative side, let's use 1,000 again, but negative 1,000. So this is going to be 999 over 2,000. They're both going to be negative numbers, so the fraction is going to be positive. So as x gets really big in the negative direction, this also is going to approach 1/2. So that's the function. Let's take a look at how it graphs. Check this out. Over here, as x is getting really, really, really big, the function is approaching 1/2. As x gets really, really big in the negative direction, x also approaches 1/2. So on the graph, we have this horizontal line, which we call a horizontal asymptote. And that is the line that this function approaches as x gets unbelievably large or unbelievably small, positive or negative infinity. And so you can see this on the graph. If you put this function in your graphing calculator or use Desmos or any other graphing tool, you're going to see this graph. In fact, you can sometimes program those tools to actually show you the asymptotes if they exist. Okay? So in this case, we have a limit. Let me grab my pen. So let's write that as a limit. F of x as x approaches infinity, and I'm going to put a little positive there just to be really clear. We're approaching infinity from the positive side, x plus 1 over 2x, that's going to equal 1/2, and also from the negative side. So now we have a function that has a limit at infinity. Okay? Now we can never quite get there, but we can get really, really close. Okay, here's a couple helpful rules for analyzing functions at infinity. So if we have the limit of this function, so this is general, we have our x as our base and we have r as our power. And just to be clear, r is a positive real number. That's the symbol for real numbers. So it has to be a positive real number. So no imaginaries. Okay, so as x goes to infinity, what's happening down here? The base is getting bigger and bigger and bigger. We're taking that base to some power. Okay, so that's also helping us make this bigger and bigger and bigger. So as the bottom of a fraction gets super big, if it's under 1, then the whole fraction is getting super, super small. Think about the fraction 1 over a billion. That's a pretty tiny number. So as x gets unbelievably large, approaches infinity, this function is going to go to 0. Okay? The same with approaching infinity from the negative side. This number is going to be negative as x gets unbelievably large in the negative direction, but again, it's under 1, so this is getting smaller and smaller and smaller. It's approaching 0 from the left side. Okay, let's do an example using these ideas. So here's the limit as x goes to infinity. And just to know, I dropped putting the positive there. If there's no positive there, you assume you're approaching it from the positive side. The function here is just 4 minus 3 over x squared. So before we can evaluate this, we need to go back to operations with limits. This expression can also be written, let's do that here, as the limit as x goes to infinity of 4 minus the limit as x goes to infinity of 3 over x squared. So now we have 2 limits to evaluate. Now check this one out. This is a constant. Doesn't matter what x is doing. There is no x in that expression, so this limit is just 4. Now let's take a look at this limit. As x goes to infinity, the bottom of this fraction is going to get ginormous, right? It's just going to get super big. Doesn't matter that there's a 3 on top of it. The whole thing is still approaching 0. So this is going to be 4 minus 0, which is just 4. So this limit is just 4. So now you can see the flavor of this kind of a limit calculation where you're looking for the thing to approach 0. Then you have a limit. Okay, let's analyze a little bit more of a complicated limit. So here's our function, minus 2x plus 3 over 3x squared plus 1. Looks a little complicated. How do we know what's going to happen with this function when x goes to infinity? Well, there's a little trick. We're going to simplify this down so we can quickly and easily figure out which terms go to 0 and what's left after that. Okay? So here's the trick, and this is just something you want to remember. Look for the highest power in your denominator. So I've got a squared there, I've got an x squared there. So what we're going to do is we're going to divide this whole expression by x squared, top and bottom. So we're not changing anything, we're just dividing by a version of 1, but it's going to allow us to rewrite this in a way that we can analyze the limit. So let's just do that. I'm going to do a quick little plug-in step. Minus 2x over x squared plus 3 over x squared all over 3x squared over x squared plus 1 over x squared. So I just divided every single term in this function by x squared. And now we can reduce down and we'll get to a point where we can evaluate the limit. So watch this. Minus 2x over x squared ends up being minus 2 over x. Let's bring our fraction bar across. Plus 3. I can't reduce that down, but that's going to be okay. Now this one's going to cancel down. The x squareds go away, so I have 3 plus 1 over x squared. That's a squared. Okay. So now we can analyze this. What happens when x goes to infinity? So I'm just going to write this step here. We know that when x goes to infinity, this term is going to get smaller and smaller and smaller. It's going to approach 0 from the left, so the limit of that is going to be 0. This one, real similar. It's positive. It's approaching 0 from the positive side. But as x squared gets super big, even though there's a 3 on top, this is going to get super small. It's going to approach 0. So the top of this fraction is going to be 0. We need to finish analyzing it. We need to look at the bottom just so we know what the result is. So 3, there's no x in that, so 3 is going to stay 3. And 1 over x squared, as x gets huge, unimaginably big, that's going to be 0. So our limit here is going to be 0 over 3, which is just 0. So that's how to find the limit of a more complicated function. Okay, here's one for you to try. Very similar to the one I just put up on the board. So what I'd like you to do right now, pause the video, use that same trick to manipulate this big fraction into lots of little fractions and analyze the limit. Okay, let's see how you did. We're going to divide by x squared over x squared, just like before. Now I'm going to write my new fractions. I got minus 2x squared over x squared plus 3 over x squared. On the bottom, I'm going to get 3x squared over x squared plus 1 over x squared. Now let's see what happens to our fraction. These are going to cancel, right? The x squareds go away, so I have a minus 2 there. And then what happens to 3 over x squared? We know from that last problem that as x squared gets really ginormous, this fraction is going to go to 0. So this is going to be plus 0 on the top. And now on the bottom, my x squareds are going to cancel as well, and I just have my 3 here. And what happens as x squared grows unimaginably large? This little fraction goes to 0. So now I have my simplified fraction, and this is just going to end up being negative 2 over 3. Okay, so there's the limit for that one. Now, look at that limit, and look at the original function, and tell me what you see. Check this out. These are both squareds. So we know from this division process that they're going to get treated the same way, and they're going to wind up as minus 2 over 3. These two are lower order terms. They don't have as high of an exponent on them, so they're going to get zeroed out by these fractions. So even if that was 3x, it would still get zeroed out because you'd have an x there and you could cancel down and you'd still end up with a 0 there. So you are on the hook to show me this process, and some functions you're going to need that. But you can take a look at your original function and you can make a very good educated guess as to what your limit ultimately will be. Okay, one more for you to try. So check this one out. Limit as x goes to infinity of negative 2x to the third power plus 3 over 3x squared plus 1. Same trick to get started. So go ahead and pause the video and let's see where you get. Okay, let's see how that worked out. So same trick. I'm just going to divide by x squared over x squared, just like before. That's divide. And I'm going to write my new fractions. We get minus 2x to the third over x squared plus 3 over x squared, all over 3x squared over x squared plus 1 over x squared. So that's your plug-in step. I urge you, resist the temptation to start canceling as you go. Just show more steps is always a good idea. So let's do that canceling. So this one's going to cancel a little differently. Check it out. I have a cubed up there and a squared down below. So we're going to lose the bottom term, but we're still going to have a 2x right there. This one is going to just stay. This one, we're going to cancel out our x squared, so we're going to wind up with 3 down below. And then we have 1 over x squared. So now let's carefully analyze what we have here, because this is going to give us a different result. If you haven't worked the problem through, then pause the video right now, think about that, and figure out what your limit's going to be. Okay, so let's write this out. As x goes to infinity, 2x is going to be twice infinity, or negative 2x. So we're going to have negative 2 infinity right there. This is not going to 0. This is going to negative infinity in the left direction. Now this term goes to 0, just like the other ones. So now we have plus 0 over there. Now let's take a look at the bottom. We have a 3, no x there, so that just comes over. And this goes to 0. Now what do you think about that? I have negative 2 infinity over 3. What's that ultimately going to be? That's going to be negative infinity. The top is just going to grow to the left in the negative direction. Unbounded, gets as big as it wants. You can divide it by 3 for sure, but it's still going to keep growing towards negative infinity. So if you recall from a prior lesson, when you have a function that grows unbounded, which is what this does, then there is no limit. This is ultimately going to be negative infinity, this expression, as x gets really big. So there's no limit for this one. No limit. Okay. So there's 3 cases here. The 3 examples we just did. You could find one that has a limit of 0. You could find one that has a fraction limit based on the coefficients of your terms, top and bottom of that fraction. And you can have one that doesn't have a limit because it just grows and grows and grows towards negative or positive infinity. Okay, let's sum that all up. First, one vocabulary word that you probably had before, but let's just make sure it's clear. When we talk about the degree of a polynomial, which is just an expression like 6x cubed plus 2x squared minus 9, or something like that, when we talk about a polynomial's degree, the degree is the number of the highest power. So if it is 6x to the third plus 2x squared minus x plus 7, the degree of this polynomial is 3. It's just the highest power in the expression. That's all that is. So this is degree equals 3. Okay? If this was a 5, then the degree of that polynomial would be 5. Okay? So the degree is helpful when analyzing a limit with a fraction in it. So the numerator degree, remember we're numerator over denominator. The numerator degree is less than the denominator degree. The limit is 0. And remember, that's because the denominator is growing really fast. That's the bottom of the fraction. So as the bottom of a fraction approaches infinity, the whole fraction approaches 0. So we had a limit in this case when the numerator degree is less than the denominator degree. When they're equal, then the limit is going to be the coefficient of the highest power numerator and highest power term in the numerator and the highest power term in the denominator. So you're going to get a limit that's just that little fraction. We did that. That was our second example. Now the last case is when the numerator degree is bigger than the denominator degree. In other words, the top of that fraction has a higher power. There's no limit in that case because the numerator grows fast. It's on the top of a fraction. So as the top of the fraction gets unbelievably big, the whole fraction also gets unbelievably big. Now that you've watched the video, jot down some notes, some questions, or a quick summary of the lesson. You can also re-watch the portions of the video that challenged you the first time. If you enjoyed the video, please click like. If you'd like to help me grow my YouTube channel, please click subscribe.